Algebra 2, Chapter 6, Section 1, Integer Powers and the Exponent Rules. In this video, we're going to cover a lot of ground, so bear with me, it may be rather lengthy. First, let's think about multiplication. Multiplication is a shorthand for repeated addition. We learned this long ago, so instead of having to add 2 to itself 5 times, 2 plus 2 plus 2 plus 2 plus 2, we can simply do 2 times 5 to get the answer of 10. Similarly, exponentiation is a shorthand for repeated multiplication. Okay, so 2 times 2 times 2 times 2 times 2, we can write as 2 to the 5th power, which is 32. In this case, 2 is called the base of the base, and 5 is the exponent of the exponential expression. So the exponent goes up here in the superscript, and the base is the part that is below. We also call this the power. Unlike multiplication, where we could multiply in either order and get the same answer, order matters in exponentiation. Okay, so if you think about multiplication, 2 plus 2 plus 2 plus 2 plus 2 is the same as 5 plus 5. Okay, but 2 times 2 times 2 times 2 times 2 is not the same thing as 5 times 5. So 2 to the 5th power is not equal to 5 squared. 2 to the 5th power was 32. 5 squared is 25. These are not equal. So let's talk about the different rules that we have. First, we're going to focus on multiplying and dividing powers that have the same base. Okay? Because we can multiply 5 by itself twice and then multiply 5 by itself 3 times, and that's equivalent to dropping the parentheses and multiplying 5 by itself 5 times, we can write that as 5 squared times 5 cubed is 5 to the 5th. That sort of shows the following rule is true about exponents. Any base to a power n times the same base to the power m is equivalent to the base to the sum of the powers. Okay, so if we're multiplying the result of two exponentiations that have the same base, this is equivalent to that base to the sum of the powers, or the exponents. So let's practice using that rule. Write using a single exponent. So q to the 5th times q to the 7th would be the same as q to the 5 plus 7, which is q to the 12th. 6 squared times 6 cubed would be the same as 6 to the 5th. 2 to the n times 2 to the m would be the same as 2 to the n plus m. Remember, we just add the powers, same base. 3 to the n times 3 to the 4th is 3 to the n plus 4. Add the powers. Okay, so we don't need parentheses here. It's implied because it's all in the superscript that you do this first. This is equivalent to 3 to the n plus 4 using the parentheses. And last but not least, this is the same base. And so we can write this as x plus y to the 5th power. And we can apply this rule the other direction, since it's an equivalency. Write as a product. Well, we can split the power up as two exponentiations multiplied together, which would be a product. 5 squared times 5 to the a, x to the r, x to the 4th, which we might reorder as x to the 4th, x to the r, y to the t times y to the c, and here z plus 2, we're going to split up the exponent, not the base. Same base, z plus 2 to the z times z plus 2 to the 2. As an aside, here's a case where it's really important to cross your z. you don't cross your z in your handwriting, there's no way you're going to keep track of the 2's and the z's. Similarly, because 5 times 5 times 5 times 5 times 5 divided by 5 times 5 is the same as just 5 times 5 times 5 by canceling, right? We can cancel these common factors. Then 5 to the 5th divided by 5 squared is just 5 cubed, and that shows the following rule for division. If we have the same base, b, and we have two different exponents, that's equivalent to writing the base to the power of n minus m, the subtraction of the two powers. Let's practice that. So q to the 7th over q to the 5th is equal to q squared, 7 minus 5. 6 to the 7th over 6 cubed is equal to 6 to the 4th, 7 minus 3. Here we have 3 to the n minus 4. Pi is just the number, so we have pi, 5 minus 3 is 2, pi squared. And here, these are the same base, c plus d, so we're left with c plus d to the 8 minus 2, which is 6th power. So what happens if we take a power to a power? So if we have 5 squared, all of that cubed. Okay, really this is raising the exponentiation, the result, to another power. So this is the same as repeating this 5 squared cubed to be the same as multiplying 5 squared by itself 3 times. And then applying the rule where we have the same base, we need to add the exponents to combine 2 plus 2 plus 2. And if we remember the definition of repeated addition is just multiplication, we can write this as 5 to the power of 2 times 3, which of course is 5 to the 6th power. Because of this logic, the following is true. The result of an exponentiation to the nth power is the same as that same base to the m times n power. So we can multiply the powers. Now note that this is not equivalent to a to the m to the n. In this case, m is being raised to the n power, and then a will be raised to the result. We're doing the order differently. So in this first case, we have a to the m, all that then to the n. This is m to the n and a to that power. Okay, so we could write this as this 5 squared cubed is not the same as 5 to the 2 cubed power. Okay, because 2 cubed is 2 times 2 times 2, which is 8. Okay, so this would be 5 to the 8th power. And this would be 5 squared cubed, which using this rule is 5 to the 6th power. Okay, so these are not the same thing. So write with a single exponent. Q to the 7th, all of that to the 5th. Well, we need to multiply the exponents. Q to the 35th power. 7 to the p cubed would be 7 to the p times 3, which we'll probably write the 3 first. So be better than the variables first. 7 to the 3p. Y to the ab. 2 to the xx, so x times x, which would write as x squared. So here we have an example where we have a superscript on a superscript. Okay, x squared happens first in this case. Then we take the result of that as the power for this exponentiation, 2 to that power. So if x were 3, you would have 3 squared is 9, 2 to the 9th power, 3 times 3. X plus y squared, then all cubed, would be x plus y to the 6th power, 2 times 3. And the last part, f, r minus s, would be to the tz power, multiplying the exponents again. Well, so that was all rules about a common base. What if instead of the base being common, we have a common exponent? Okay, so in this case, we have the exponent of 2 being common in both cases. So if we think about what this means, it means repeat the multiplication by this exponent. So we'll have 5 times 5 all time, and then that times 4 times 4. We can reorder multiplication, so we can make it 5 times 4 times 5 times 4. And this is the same as 5 times 4 squared, because we repeated this multiplication. And because of this logic, we could apply this to any number, and we derive the following identity, which is 1 base to the exponent n times a different base to the exponent n is the same as multiplying those bases first and then taking the exponent n. Now note this is not true of addition. Okay, if we had a to the n plus b to the n, we can't combine that in any way. It's only true if we're multiplying the result of these exponentiations. So write the following expressions without parentheses. So that would mean apply the rule we just were talking about. We'd have q to the 7th, p to the 7th, 3, and this is kind of using it backwards, but it's still good practice. 3 to the n, x to the n. Here we have 3 things, so we can cube each of them would be cubed. So we'd have 4 cubed, a cubed, and b squared cubed. B squared cubed. Okay, now applying the rule about power to a power, we would have 4 cubed, a cubed, b to the 6th, because we multiply 2 and 3. Now we might write 4 cubed as 64 instead of as 4 cubed, since it's easier to understand 64, or to compare 64 with some other number than comparing 4 cubed. Here we have 2 times x to the 2n to the 3n. Okay, so we can, this is a multiplication, 2 times all of this. Okay, so breaking up the parentheses, we need to apply this 3n to the 2 as an exponent, and we also need to apply it to x to the 2n. So we need to write x to the 2n in parentheses to the 3n. And then remember the multiplying rule, and we can write this as 2 to the 3n x, 2n times 3n is 6n squared. And applying the rule forwards, write with a single exponent. Okay, so here we're going to try to combine using a single exponent. So using the rule a to the n times b to the n is equal to a times b to the n. So here we have c times d all to the 4th power, 2 times 3 all to the n power, which we could write 2 times 3 is 6, 6 to the n, 4x squared. So here we need to think about 4 being as a power. 4 is 2 squared. We want to make it the same power, so we can use the same exponent rule. 2 times x all squared. Here we have something to the 4th, something else to the 4th. So we have a times b plus c, all of this to the 4th power. And again, different insides but same power, we can write them as a multiplication, x squared plus y squared times c minus d, and then all of that to the 5th power. Now, what about division? So if we have the same exponent but we're dividing the exponential expressions instead of multiplying, well, the same logic holds. We can write 5 times 5, 4 times 4. We can split the fraction so that we're doing the division first, because we can reorder division and multiplication without changing the expression's value. And then we can write this as 5/4 squared. So we can see that a to the n divided by b to the same n power is equivalent to doing the division first and then taking the exponent. So let's again practice. Write this without parentheses. It would be 4 squared over 5 squared, which we could write as 16 over 25. Here we have c to the 12th over d to the 12th Here we have y fourth over z cubed to the fourth power. So we multiply the exponent, z to the 12th. If that's skipping a step for you, write it. Instead of skipping the step, write it out. Z cubed to the fourth. And then remember the rule about if we have this exponentiation raised to a power, multiply the powers, or multiply the exponents. Here we have 2u cubed. Don't forget to cube the 2, and 3v cubed, which is equal to 2 cubed, which is 8u cubed, and 3 cubed, which is 27v cubed. Write with a single exponent. So these are the same powers. We can apply the same exponent law with fractions or division to get 3/7 to the 5th, to get q over p to the 7th. Here we need to think of 9 as 3 squared, 3x over y all squared. P plus q to the 4th over z to the 4th we can write as p plus q over z all to the 4th. Then we can write this as x squared plus y squared over a plus b all to the 5th. So what happens if we have a 0 for an exponent? Well, think about this. 3 squared divided by 3 squared is of course just the same thing as 1, because any number by itself divided by any number by itself is 1. And if we think of the subtraction rule for the same base, we would have 3 to the 2 minus 2, right? 3 to the 2 minus 2, which is 0, 3 to the 0th. So it makes sense that 3 to the 0th power is 1. And for this reason we define a to the 0th power, so whatever a is to the 0th power is 1, as long as a itself is not 0. Why that exception? Because that would yield this fraction, which of course is meaningless. So we have a division by 0. So any number other than 0 to the 0th power is 1. And also we can think about, what about if we had the numerator with a smaller power than the denominator? Well, 3 to the 1st over 3 squared would be the same as 1/3. And if we subtract the exponents, 1 minus 2 is minus 1, which would also be the same as 3 to the minus 1 power. And that yields the following rule. A to the minus n is equivalent to 1 over a to the n, as long as a isn't 0, so we don't end up with a division by 0. And we can extend this by thinking of the rules of complex fractions. If a were really a fraction and you had a negative exponent, then you'd have 1 over a over b to the n. Okay, and using the rules that we already know, we can derive this truth, which is that if we have a fraction, a over b, to a negative exponent, then we can flip the fraction, invert the fraction, and remove the negative, or negate it if it was positive, change the sign. And of course, this works with 1, so if you have a to the minus 1 power, that's the same as 1 over a to the first power, which is just a. Okay, so often when we're talking about inverse or multiplicative inverse, we'll use a negative 1 power to indicate to take the inverse, or to take 1 over that number. So let's practice. 5 to the 0, well, remember 5, any number to the 0 other than 0 is 1. 3 to the minus 2 is the same as 1 over 3 squared, which is 1/9. 2 to the minus 1 is the same as 1 over 2, or 1/2. Here we have minus 2 to the minus 3, which would be the same as 1 over minus 2 cubed, which is negative 1/8. And here we have 2/3 to the negative third power, which we can flip the fraction to 3/2 cubed. Okay, 3/2 cubed is 3 cubed over 2 cubed, which is 27/8. Rewrite with only positive exponents. Assume all variables are positive. So to change the exponent to be positive, we can invert the part with the negative exponent. So here the 3 has not got an exponent. This is 1 divided by 3 times x to the minus 2. So this would be equaled 1 over, and I'm going to do this the long way just to show how this works. 3 to the 1 over x squared. Okay. Now what do we do with this crazy thing? Well, we can bring the 3 in because 3 times 1 is just 3. Right? It could be 3 over x squared. Now we have the rules of complex fractions. We have 1, the numerator, times the inverse of the denominator, x squared over 3, okay, which is equal to x squared over 3. And if you remember just the general principle, if we're doing a multiplicative inverse, if it's on the bottom, pull it to the top. If it's on the top, pull it to the bottom and change the sign. That's the pattern that you need to use, and it's faster than writing all these steps out. X over y to the negative third is just the same as y over x cubed, using the second version of the negative power rule. First, let's deal with these parentheses. So we need to use the rule about the common power. 3r to the minus 2. The common power would mean we have to take 2 to the negative fourth and r to the negative fourth. Okay. So like I was saying, if it's negative, pull it up. If it's on the bottom, pull it down if it's on the top. So you'd have 3r to the fourth times 2 to the fourth. So pulling r to the fourth and 2 to the fourth up over r squared. Okay. Pulling r to the negative 2 down. Now if we remember our law of exponents, remember we can reorder the multiplying and division all we want. So we can remember our law of exponents where we subtract with a common base, subtract the exponents. So that gives us 3r squared, 2 to the fourth. And of course we wouldn't write this way with these two numbers. We would multiply all this out and get a number. Well, 2 to the fourth is just the same as 4 squared, which is 16 times 3, which would be 3248 r squared. So here we can go up and come down at the same time to get rid of the negatives, but we can also go ahead and use our common base rule. This is the common base, so we can take negative 2 and subtract negative 5. A plus b. Negative 2 minus negative 5 would be negative 2 plus 5, which is 3. And we already have a positive exponent. We're done. This is clearly easier to just do the flipping the fraction and changing the sign of the power. Same with this one. We don't need to bother getting rid of the parentheses. We'll just flip the fraction, invert the fraction, and invert the sign of the exponent. And we're done. We have written it with a positive exponent.